Okay, so in the previous video, I showed you the property of the covariance when you linear transform the original random variables. The result is intuitive, but it's not desirable. The covariance is not as a measure of the relationship. It changes as the measurement unit changes, so it's not a desirable property. So as I said, we would like to standardize the covariance, and we would like to construct a new measure that does not change even when the measurement unit changes. That is the correlation coefficient. And the idea is simple. You know how to standardize a variable. So earlier, we used deviations only, but so these deviations change when you change the unit, measurement unit. So now the idea is let's standardize those deviations, right? Excuse me, like here, where is the formula? So here, we use those deviations, but replace the deviations with their standardized versions. That's the idea. Then as you see, exactly this part has changed, and the new thing is the standard deviation. So denominator has standard deviation, and then as you can see, those standard deviation can be factored out, and then without the standard deviations, this part is covariance, and just it's like standardizing the covariance with both standard deviations, right? So because there are two variables involved in the covariance, so you have to use both standard deviations to standardize the covariance. Then as a result, mathematically, what's nice about this new measure, the correlation coefficient, is that the correlation coefficient always lies in between -1 and 1. So you know its scale is fixed. -1 is the strongest relationship to the negative side, and +1 is the strongest positive relationship. So and 0 is no relationship. So you see where your data lies in this spectrum, right? So it's uniform, and as I said, even if you change the measurement unit, the correlation coefficient does not change. That's the new property of the correlation coefficient. As a result, the correlation coefficient captures the strength of the relationship as well as the direction. The sign of the correlation coefficient captures the direction, and its absolute value captures the strength. Remember, covariance, the magnitude of a covariance doesn't mean anything because it depends on the unit. By changing the unit, you can make covariance like several thousand, several million, or 0.000 something. So the size of the covariance depends on the unit, so you cannot tell how big or how small the covariance is. But now the correlation coefficient has fixed scale, so it gives you the strength. It tells you about the strength of the relationship. Okay. Idea is again simple. Standardize the covariance. That's basic idea. And look at this. This is the same graphs I used in the first video today. So at the time, I explained its strong relationship and its weak relationship. So their difference is coming from the correlation coefficient. This weaker graph has a correlation coefficient of 0.5. As the correlation coefficient increases near to +1 or to -1, in this case, it's positive, so increases to +1, then the observations become like tighter. The deviations become smaller, right? So the trend line is a better fit, a more powerful predictor of the observations. So correlation coefficient can contrast these two differences, the differences between these two graphs. On extreme example, maybe it helps you to understand. So if you observe a data that has a perfect straight line, so all the dots are aligned in a perfect straight line, then that correlation coefficient is either +1 or -1, depending on it's upward sloping or downward sloping. So, right, it's so this is the perfect relationship, strongest possible relationship. And these examples are more like a warning, so special cases. So correlation coefficient can be 0 in several cases. Right? So correlation coefficient can be 0 when the trend line is flat. So clearly slope is 0, but also in this example, trend line is vertical. Still, we think it as 0 correlation coefficient. Very strange, right? Or simply there is no pattern. Like in this case, it's hard to make a straight line. You can think it as a flat line, but also you can anyhow. So there is no clear pattern. That's also correlation equals to 0. And finally, correlation coefficient also captures linear relationship. So if the underlying relationship was nonlinear, then still correlation coefficient could be 0 because of nonlinearity. There is a very strong, clear relationship, but that is not linear. So correlation coefficient cannot explain that. So this is another example. So anyhow, correlation coefficient of 0 is simply means the trend line is flat or there is no pattern. When x increases, y does not increase or decrease at all. That's the intuition. Okay, then coming back to our numerical example. So think about this. We know that the covariance was minus 150,000, right? So then, to calculate from the covariance, to calculate the correlation coefficient from the covariance, what we need is just their standard deviations. Standard deviations should be calculated to obtain the correlation coefficient. And remember, because we used the sample covariance formula, you have to match the formula for the standard deviation. So here, we calculate the standard deviation using the sample formula, denominator n-1, because the covariance was calculated with denominator n-1, right? So if you had population formula for the covariance, then you have to apply the population formula for standard deviations too. So basically you have to match the formulas, right? So that you have consistent correlation coefficient. And then standard deviation of x, if you calculate, I'm going to skip that. If you calculate standard deviation of x, it is 15. And standard deviation of y is a strange number, 13,000 something. So anyhow, if you use a calculator to calculate the correlation coefficient, what you're going to do here is covariance is standardized by multiplication of those two standard deviations, right? 15, which is standard deviation of x, and 13,000, which is the standard deviation of y. And then if you calculate them, it becomes minus 0.7559 something. So as I said, correlation coefficient lies between -1 and 1, +1 and -1, and this is negative, of course. So the direction is negative, and the strength is 0.75, which is closer to -1, right? It's pretty strong correlation coefficient, right? Okay, then it's your turn to calculate the correlation coefficient. Now you, as before, you use the Fahrenheit temperature and GDP per capita in dollars, in $1,000. So use those numbers and try it by yourself to calculate the correlation coefficient between these new random variables. Okay. Okay, so the answer is the algebra must be tedious. So it will take time. So if you have not finished yet, please stop the video. The answer is A. First, because we know that the correlation coefficient should not change when you linearly transform the random variables. So the original correlation coefficient must be the same to even after the transformation from Celsius to Fahrenheit and from dollar to $1,000. Both are linear, so there should be no difference. The answer is A. But however, if you follow the same algebraic steps as before, then standard deviation of the new random variable can be calculated, which is 27, and standard deviation of z can be also calculated, and then it is 13.229. So when you calculate the standard deviation of the new random variables, you may use the result from chapter 4. Standard deviation of a linearly transformed random variable is affected only by the multiplied coefficient. Plus b does not affect. So if you multiply a and add b, then standard deviation is affected only by multiplication of a. That's what we learned in chapter 4. So it will be useful in calculating the standard deviation. Once you calculate the standard deviation, either way, just calculate from the scratch or using this formula, you should get these numbers. And then correlation coefficient is the covariance standardized by these two standard deviations. No difference, as it should be, right? There should be no difference. And as I said, the underlying relationship is the same, remains exactly the same. So the direction of the relationship is still negative, and also the strength of the relationship does not change either. So all the results are pretty straightforward. Okay, so now I'm going to show you how to do it on Excel with the real data. So this is the real data I introduced. So this is using Fahrenheit and GDP per capita, and I made another data set based on the same data, but it's in Celsius and in dollar. I did not transform the GDP per capita. So let me show you how you calculate the covariance. Go to formulas, and I'm going to insert formula, which is based on covariance. If you search for covariance, you will see these two. Actually, this is, I think, obsolete, right? Available for Excel 2007 or earlier, so it's obsolete. So there are two formulas. As you know, .s means sample formula, and .p means population formula. Let me try both of them. First, covariance.p array 1. Array 1 will include the temperature observations, right? And array 2 will capture the GDP per capita. in this way. If you click OK, it gives you minus, so P covariance is minus 50, nearly minus 66,000, right? And let me calculate sample covariance. Excuse me. You can just do it, covariance dot S, and B, column B from 2 to B 184. I remember the range. And C2 to C 184. Then you get sample covariance, which is slightly different. Okay? So the difference is coming from the difference in the sample variance and the population variance formulas. And you can calculate correlation coefficient. Correlation coefficient formula is CORREL. So correl, include that. And then again, array 1 is B2, B184. And so C2, that's C184. Okay. So if you calculate that, correlation coefficient equals minus 0.31. So in the full data set, the relationship is still negative. But the strength of the correlation becomes much weaker. Like it's like 0.3, around 0.3, which is much closer to 0 than minus 1. Okay, just a checkup. If you want to check if this correlation coefficient is correctly calculated, I will calculate standard deviations. I will calculate population standard deviation, sample standard deviation for temperature and for GDP per capita, right? So let me calculate the standard deviations. We know standard deviation formula is STDEV dot P. So then, again, so do it this way. And I will simply drag it to here. Then, oh no. Oh, excuse me. It does not need 2 columns. Excuse me, it's my bad. Okay, so standard deviation does not need both at the same time. So we have standard population standard deviations and sample standard deviations. You can just change to S. Oh, excuse me. You can change standard deviation to S and redefine area. Okay. Look at this. So I calculated standard deviations for each variable using 2 formulas, and we know the covariance must be calculated. The correlation coefficient should equal to covariance divided by these 2 standard deviations. Okay, covariance F2 is covariance divided by multiplication of these 2 standard deviations. Then you get the same number, right? And this number is based on population covariance, population standard deviation for both variables. But now let's try the sample formula. Sample covariance divided by sample standard deviations. Then you get the same thing. They are identical, right? Exactly the same. They are, even in the deeper decimal places, they should be the same, identical. Okay? And finally, let me just simply check if the covariance and correlation coefficients are the same when you use the Celsius measure, right? Covariance P is defined here, comma, here, these two variables. So look at this, covariance is minus 36,000. Now that is different. Earlier it was how to see, minus 66,000, but after you change the Fahrenheit into the Celsius, it becomes minus 36. So this is population covariance. And in sample covariance, it's similar but also different from the Fahrenheit case. However, if you calculate correlation coefficient, excuse me, like this, the correlation coefficient is the same. So as you see, correlation coefficient minus 0.310 minus 0.310, and decimal place is the same. So so this Excel experiment can show you what's invariant and what is variant. So you have to understand how those measures can be interpreted and when they are used. Okay, thank you for watching. I'm going to use a different example in the next video. Bye bye.